Thanks, everyone. So as Jane mentioned, I'm Safia. You can find me as Captain Safia everywhere on the internet. Twitter, GitHub, DeviantArt, probably Neopets too. Or you can visit my website, which is safia.rocks. As a bit of a content warning to everybody, this is a technical talk, but there is no code or demos. So if you come to conferences to see semicolons and curly braces on a really big screen, I'm so sorry to disappoint. But that being said, it'll be fun nonetheless. If you're sitting towards the back, or if you have some sort of visual disability, if you visit j.mp/js-mem-live, you can follow along live with this talk as I go through the slides, and skip ahead if you'd like to too. So I'm a bit of a computing history buff, so I'm going to start this talk all the way back in 1936, when a young man by the name of Alan Turing theorized the concept of what's known as a Turing machine. Alan Turing was a brilliant mathematician. He actually helped the Allies win World War II using his amazing math and science skills. And the Turing machine was a simple abstract machine. You can see a physical rendering of it here. And it essentially processed bits on a strip of paper using a set of rules that were loaded into that big central box. You can think of it as the first ever CPU. Now, a couple of decades later, there was another smart guy by the name of John von Neumann, and he theorized what's known as the von Neumann architecture, which basically said that a computer was something that had inputs and outputs, it had a central processing unit, and it had a separate space for long-term and short-term memory. And these were the sort of two early conceptualizations of what a computer was. Turing's idea was remarkable. A machine that can think is remarkable. Von Neumann took it further. A machine that can remember what it thinks is revolutionary. And if the past 80 years of history have been indicative of anything, a machine that can think is indeed revolutionary. And today I want to talk about the work that computers do to remember, how they manage memory, how it can build memory-performant applications in JavaScript and Node. And you're probably wondering, why do we care? It's 2016, my laptop has 16 gigabytes of memory. Is this really a problem in this day and age? And the answer is yes, it is, and yes, you do need to care. Because although the amount of available memory in machines has increased rapidly over the past 40 years or so, so have people's expectations and demands of what machines can do. People demand web experiences that require a lot of memory-intensive render and compute tasks, and you have to work around that. And the other thing is that not all your users are using the latest, sexiest tech, right? Not everyone has access to the latest technology, but that shouldn't inhibit them from having the same web experiences that all your other users do. And the last reason is a matter of pride. You don't want to be that app. You know that app? The one that takes up so much memory you have to close Windows, the one that takes up so much memory that it forces all of the other tabs in the same process to shut down. Nobody wants to use that app. Nobody wants to write an app like that. You don't want to subject your users and customers to that kind of pain. And to do that, you're going to have to go to class and learn a bit about memory management. The first thing that we're going to do is learn a little bit about what's known as manual memory management. And I think I saw a couple of people in the audience start to cry because they know what I'm about to talk about. So if you've programmed in a low-level programming language like C, you're familiar with you're familiar with manual memory management. What this basically means is that every time you want to use something, say a list of names of wines in a restaurant, that's kind of the data that you want to use. You're going to need to manually allocate space on your machine for that data before using it. And when you're done using it, you have to manually clean up that space yourself. It's an explicit process. You can imagine this is frustrating. It's no fun. We're not made to manage data ourselves and keep track of it. It's painful. You get code that's filled with errors and memory leaks and all sorts of other nasties. But thankfully, in the JavaScript world and in tons of other programming languages, that's not the problem that we have to worry about. Because we have something known as automatic memory management or garbage collection. And it's kind of obvious in the name, but automatic memory management is the process of automating the process of allocating memory and then clearing it up when it's no longer being used. And garbage collectors are generally provided by your programming language implementation. They take care of figuring out when memory is no longer active or being used and cleaning it up. They've got all sorts of smart things to do it efficiently. And the garbage collection technique that we're going to look into specifically is the one provided in the V8 JavaScript engine. There's tons of other JavaScript engines, of course, but we're going to talk about V8 specifically because it's the implementation used by Node. It's also the one used in Chrome, so it's relevant to front-end and back-end people. Bringing us all together. Awesome. So memory is allocated into what's known as a heap data structure. You start off and you have a root object. In this case, it's that red node. And it points to other objects that are being referenced. The green nodes are scalars. Those are always the terminating nodes in our heap. This is what the node, a memory heap looks like. And memory in V8 is allocated into different spaces, depending on different kinds of properties. I'm going to go through these properties really quickly. So the first space you have is the new space. This is where memory is first allocated. Data in this space is generally pretty small, and once it's hung around the new space for a while, it graduates into two different spaces. If it's a pointer or a reference to a scalar, it gets moved to the old pointer space. And if it's data in and of itself, if it's a string, if it's a box number or an array, it gets moved to the old data space. And there's a fourth kind of space separate from those two, and it's known as the large object space. The name is also pretty obvious. It stores large objects, generally larger than 8 megabytes. And then the fifth kind of space is known as the code space. In the code space, you have code instructions that are compiled just in time. The main distinction between the code space and the other spaces is that the memory in the code space is executable memory, meaning you have permission to execute the data in the space, since code is data. You obviously don't want that in any of your other spaces, because somebody could put a nasty in their data and do lots of bad things. People use computers for terrible things I never knew. So that's how we allocate objects into memory and some of the heuristics that are used to identify what places in memory they should be allocated. So we've got them allocated. We're programming. It's super fun. We're changing the world, saving people, building unnecessary node modules. Who knows? But remember, this is garbage collection, so there is a cleanup process involved in that allocated memory. How do we know when something needs to be cleaned up? And the concept that we use to determine when a piece of memory is garbage is known as reachability. And the idea is pretty simple. A piece of memory is considered garbage if there is no way to get to it by traversing from the start of the heap at the root object. So if you're looking at this particular memory heap, these two lonely pairs would be considered garbage because there's no way for me to start at the root object in red and traverse to them. They're just lonely and isolated, kind of like me. Dark joke, sorry. No, I'm not lonely and isolated. I have all you guys. And so we've kind of covered this general idea of garbage collection. We've covered some of the heap structure that's used and some details about V8. But how exactly does it collect garbage? Well, V8 employs something called the stop the world garbage collection technique, which means whenever it needs to clear away unused memory, it's going to pause the running program and execute that garbage collection cycle. And you might imagine that there's some performance setbacks to this, obviously. This is made better by the fact that most of these garbage collection cycles, where you halt and then run a garbage collection cycle, happen in short chunks of memory, so that you're not running a really long garbage collection cycle on a huge piece of memory for a really long time. You're just doing it in bursts. And you can optimize it even further by running a garbage collection in an instance of idle compute time to take advantage of that wall. And this process kind of repeats. You allocate memory as you program. As your memory fills up, it gets cleared away, so on and so forth. And there's a really interesting distinction that V8 takes when it's cleaning up memory. So you have data in your new space, which is smaller. It's generally newer. V8 takes one approach to clearing this kind of memory. And then you have data in your old data space. It's kind of graduated. It's matured. And V8 has a different approach to clearing away that memory. And this idea of taking different approaches or using different techniques on different kinds of data is known as a generational garbage collector. So if you want to like show off that you're smart, tell people that V8 employs a generational garbage collector. Great pickup lines for everybody. The first technique that we're going to look to is called scavenging. This is exclusively used in the news space, so it's filled with small, fresh data. And what happens is V8 goes through the root object of our heap. It traverses through it, and every time it hits an object, it makes a copy. And then it clears away what was left. And the effect is pretty simple. If anything wasn't reached in that traversal, it wasn't copied, and it was deleted when it cleared away that existing memory. The general summary of this is things are copied from a to space to a from space. If you're thinking about this algorithm, you're probably like, oh, this is kind of a really space-intensive process, because you need twice the space to execute this. This ends up not being too big a deal because the data in your new space is small anyways, so you don't have to worry about it that much. So it's totally fine. And then there's another technique that's utilized in the old data space, and it's known as mark and sweep. And it's a two-phase technique. So in the first phase, which is the mark phase, you traverse through the heap, marking all of the objects that you reach. In the second phase, you sweep, which is you do a cleanup. Now, I could go into way more details about this. The mark and sweep technique is one of the oldest garbage collection techniques. It's been modified a ton through time, but it's like 4:15 p.m. and everyone here is thinking about a big cold beer, and y'all don't want to hear that. But if you do, come talk to me afterwards, and also feel free to Google it around yourself or whatever. Now, you're probably thinking, okay, I've got this kind of knowledge of the theory of garbage collection of memory management. I have an understanding of like how it works in V8. Like, how do I start to use this practically? What kinds of questions should I ask when I'm coding to start to think about memory in my application more actively? There's two simple ones you can start off with. The first is, how much memory is my application using? It's a pretty simple one. The second is, how often do garbage collection cycles occur in my application? How often does the trash have to be taken out? And to answer these questions, you need the right tools for what can be a pretty messy job. And one of the best tools is actually right in your browser if you're using Chrome. I'm a bit of a Chrome fanatic, obviously. It's the Chrome DevTools. And I could like walk you through the screenshot of like what's going on in all this, but instead I'm going to do a quick demo. I know I lied and I said there were no demos, but I don't know if this counts as a demo. So let's try it out. Really quickly, I'm going to pull up, if I can. I'm going to exit full screen. Am I in the right place to do that? Yes. Thanks. Yay, teamwork. Okay. Awesome. So I've got the CascadiaFest website. This is terrible. Open on my machine here, and I've got Chrome DevTools open. I'm under the Profiles tab. When you hit this tab, you're going to see what's known as a heap allocation profiler that takes a snapshot of the heap in a running application. And I'm going to show you one way to use this profiler tool. So what we can do, it's a really handy feature, is we can look for detached DOM elements. These are elements that are no longer present in the DOM tree, but they're still being referenced in the JavaScript. And to do that, we can head over to our class filter here and do a look for detached. Super useful. Let's look at this one entry here. It's the first one. We can expand it. And it looks like it's a detached anchor tag. And there's tons of useful information in the columns to the right of the constructor. So you'll see what's known as the shallow size. That's the literal size of the object in memory. You'll see the retained size. That's the size of the object and all of the objects it references. It's known as the retained size because those are all the objects that it's retaining as active in memory or alive in memory. You'll see the distance, which is its distance from the root node. You'll see here at the bottom, it looks like it's defined as a free variable in system context, which is a general term for a closure. So somewhere in there, we've got a nasty closure in our application. You could use this to debug all sorts of things like memory leaks, programs that are using too much memory, and I'll actually go a bit into those in a second. Now we jump back into our presentation. This is always the awkwardest part of any tech talk where you're like, let me do a demo and switch contexts and then switch it back. So that's how you might do some profiling and debugging on memory in the front end. If you're working on the back end on the Node side, you're obviously going to need to use a different set of tools. And there's a ton that you can use. So there's MemWatch, not MemeWatch. Oh my gosh, that's so embarrassing. There's a typo in my presentation. I can turn it into a joke, that's okay. So this MemWatch, now I'm pronouncing it wrong too. So it's platform independent. It's an age of module. You can use it for memory profiling. There's Heaped Up, which allows you to take a snapshot of the V8 heap. You can actually load that snapshot into the Chrome profiler and analyze it. There's a V8 profiler, which contains the node bindings for the profiler that's used in V8, which is in C++. And if you're at a larger scale, there's tons of performance monitoring tools. I'm going to avoid promoting or endorsing anybody up on stage, but if you're curious about what kinds of tools exist, if you're working on a larger application scale, come talk to me afterwards, and I can help you. So you're probably wondering, when should I use all of these things? When should I apply all of this knowledge? Like, is this really necessary? So I'm going to go through some examples of things that you might hear from your users or your customers and explain some memory-related issues that you might want to look into. So the first is you get a user who's nice enough to file an issue or a complaint, and they say, I have your to-do list app open in my window, in my browser all the time, and then after a while, it just makes my browser crash. Why? This is textbook memory leak, meaning that there's a logical error in your application that forces more memory to be allocated over time. Chrome comes with a timeline allocation feature, which allows you to explore how memory is allocated over time and when your garbage collection cycles happen so that you can start to investigate that. Someone explains your app has jank and jitters, and Nolan explains some reasons why that might be happening yesterday. But if you're thinking about some memory-related issues that might be occurring, it might be because your application is running its garbage collection cycles too frequently. This is another time where you can use Chrome's timeline allocation feature or whatever profiling tool you have to see how often garbage collection cycles run and in what instances and what spaces are filling up faster and why. And then someone just says, like, your app just sucks. And you're just like, no, what does that mean? That's a big question. It might just mean that your application is using too much memory in general. All sorts of hairy problems. The one thing that you need to recognize is that memory behaves differently across different implementations. So the way it's cleared and processed in one browser is different from the way it's cleared and processed in another browser. And the steps you need to take when analyzing problems like this is figure out, what browser platform combinations are most popular for your users, then start to do like a dedicated debugging analysis for each of those browsers. And it might take you forever, but the results are worth it. So I guess there's that. Memory management is a hard problem. Computers have had memory since von Neumann theorized his architecture in the 40s. And they're going to have memory for a long time, and we're going to have to manage it regardless of what sexy framework we're using. Things like V8 make it really easy and include lots of optimizations that hide the internals from us. But I'm going to be a total mom right now and ask everybody to eat their vegetables and appreciate their garbage collector and understand how it works. Because sometimes it's the seemingly unsexy internals of a programming language or a platform that are the most exciting, unless I'm just really lame, which I hope not. That was the end of my talk. If you have any questions, you can either come up to me afterwards or hit me up on Twitter. If you're nervous about reaching out on a public forum, my email is safia@safia.rocks. Make sure you have a funny cat gif in there just to make it great for me. That's it. Thank you so much, everybody.